In this lecture, we are going to discuss about the torque equation in a three-phase induction motor. Whenever we are giving a three-phase supply to the stator winding of a induction motor, there is a rotating field will be creating from the stator winding. There is a rate of change of flux linkage with the rotor conductors as well as stator. Whatever the voltage induced in the rotor, which is driving a current through the rotor bar, whenever current carrying conductor places in magnetic field, every conductor experiences a force. All forces collectively driving the shaft in one direction, same direction of a stator. So here the torque is nothing but a twisting momentum at the axis of the shaft. How we are going to find the expression for the torque in a three-phase induction motor means to find the expression for the torque in a three-phase induction motor, we are considering only the rotor circuit. We neglected the stator circuit of a induction motor. What are the expression we got it here? This is very simplified expression. This is the circuit diagram for the rotor. This is the voltage which is applied to the rotor circuit. IR is nothing but current passing through the rotor. RR is nothing but a per phase rotor resistance. S into X2 is nothing but a variable leakage reactance of a rotor of a induction motor. The torque produced in an induction motor is directly proportional to the mutual flux and running rotor current and the power factor of the rotor in a running condition. The torque is directly proportional to the pi IR and cos theta R, where pi is nothing but a mutual flux. IR is nothing but a rotor current in a running condition. Cos theta R is nothing but the power factor of a rotor in a running condition. This mutual flux is directly proportional to the self-induced voltage in a stator winding. We know that in case of induction motor, the transformer ratio, it is defined as a ratio of secondary voltage to the primary voltage, K equal to E2 by E1. In case of induction motor, the secondary voltage is nothing but rotor voltage. The primary voltage is nothing but a stator induced voltage. Now, from this expression, you can say very easily that E1 is directly proportional to the pi. So, in place of E1, you can keep the pi. If you take the pi this side, then E2 is directly proportional to the pi. So, in place of pi, in a torque equation, now we have taken the E2. E2 is nothing but a per phase standstill voltage in a rotor. We know that from the circuit, IR equal to ER by RR square into S into X2. Rotor power factor cos theta R equal to RR by square root of RR square plus S into X2 whole square. Now substitute these two equations in equation P is directly proportional to E2 into this is the rotor current, this is the rotor power factor in the running condition. Now here ER is nothing but a rotor voltage in running condition. In place of ER, you can write the S into E2. To remove this proportionality, you have to keep a one constant, that is K. Now the torque developed in induction motor is equal to K into S into E2 square RR divided by RR square plus S into X2 whole square. This is very simplified torque equation in induction motor where we neglected the all stator component. Where K is nothing but a motor constant that is defined as a 3 by 2 pi ns. This 2 pi ns is nothing but a angular synchronous speed. So from this expression, you can say very easily that E2 is constant, RR is also constant. The only one parameter is changing, that is the slip of the induction. The slip of the induction motor is highly depending upon how much mechanical load we are applying on the induction. So in this expression, the variable quantity is the S. Hence the torque in a running condition is T equal to 3 by 2 pi ns into S into E2 square RR divided by RR square plus S into X2 whole square Newton meter. Suppose if we want to find out the torque developed induction motor at a starting. At the time of starting, the speed of induction motor is 0, so the slip becomes a 1. In place of slip, if you take the 1, then it gives the starting torque developed in induction motor. So the starting torque developed in induction motor is equal to 3 by 2 pi ns into E2 square RR by RR square plus X2 whole square. Again, this value also we are getting in a Newton meter. Suppose if you want to find the torque developed induction motor at full load means at a full load, how much slip is maintained by the induction motor, that value you have to take here. Then the whatever the torque we are getting, the torque is nothing but a full load. In this manner, by taking the slip at any value of the load, we can calculate the torque developed in induction motor at any value of the load. Now we want to find out the what is the maximum torque developed in an induction motor. This is the general expression for the torque developed in induction motor. Here the variable quantity is S. To find the maximum torque developed in induction motor, we have to differentiate this equation with respect to the slip and equate to the zero. That is U by V formula. You apply U by V formula, K into S E2 square RR and differentiation of the denominator minus denominator into differentiation of the numerator divided by the square of the denominator equal to 0. So, if we cross multiply this equation, numerator equal to 0. Now we have to compute the differentiation in the numerator. See here, this is the constant. So the differentiation of the constant becomes 0. Here s square is there. So we are getting a 2s x2 square. So here we are getting a one term. The same manner here also we are getting the one more term, that is 2s square k into x2 square e2 square into rr minus 2 into rrk x2 square e2 square rr square equal to 0. If we simplify this equation, we are getting s square x2 square minus rr square equal to 0. So the slip of the induction motor at a maximum torque, that is equal to rr by, where rr is nothing but a rotor resistance, x2 is nothing but a per phase rotor leakage reactance at a standstill condition. This is the slip at which the maximum torque occurs in an induction motor. That we denoted with a S suffix M. Sometimes this value also will be taken as a small a. Next, ratio between the full load torque to the maximum torque. We know the general expression of the torque developed for induction motor. In that, if you take the slip corresponding to full load, that is S suffix FL, nothing but a resultant expression is nothing but a full load torque. So the full load torque PFL equal to K into SFL into E2 square R2 divided by R2 square plus SFL X2 whole square. The slip corresponds to the maximum torque A equal to RR by, not R2, RR by, now the maximum torque developed by induction motor, P maximum equal to K into SM into E2 square RR divided by RR square plus SM into X2 whole square, where SM is nothing but the slip corresponding to the maximum torque. In this place, now we have to substitute this one, we are getting the maximum torque developed by induction motor. So, maximum torque developed by induction motor, P suffix M equal to K into RR by X2 into E2 square RR divided by RR square plus RR by X2 into X2 whole square. Here, if we simplify this one, finally you are getting the K into E2 square into RR square divided by 2 RR square. RR square gets cancelled. So finally, the maximum torque developed by induction motor equal to K into E2 square by 2 into X. So from this equation, we can say very easily that the maximum torque developed by induction motor is not depending upon the rotor resistance, whereas the slip at which the maximum torque developed by induction motor is function of a rotor resistance. Now this is the expression of the maximum torque developed by induction motor. This is the expression of the full load torque. So the full load torque by maximum torque, this is equal to, take the ratio between this equation 1 to equation 2. We are getting the K into E2 square SFL RR by RR square plus SFL X2 whole square into 2x2 by K into E2 square. Here K into E2 square, K into E2 square gets cancelled. So we have a 2 SFL RR X2 divided by RR square plus SFL X2 whole square. Now divide the numerator and denominator by X square. So here we are getting the numerator, we are getting the 2 SFL RR by X2 divided by RR by X2 whole square plus SFL whole square. RR by X2 is nothing but at a maximum torque. So the full load torque by maximum torque equal to 2 into slip at full load, slip at maximum torque whole divided by slip at maximum torque square plus slip at full load square. This is the final expression between the full load torque to the maximum torque developed in a induction. Now we're going to find out the ratio between the starting torque to the maximum torque. Already we know the expression for the starting torque. T starting equal to K into E2 square R2 by RR square plus X2 whole square. We know also the maximum torque of next Tm equal to K into E2 square by 2x2. Now we want to take the ratio between the starting torque to the maximum torque. So take the ratio between equation 1 to 2. T starting by T maximum equal to K into E2 square RR by RR square plus X2 whole square into 2x2 by K into E2 square. Again K E2 square, K E2 square gets cancelled. T starting by T maximum equal to 2 RR X2 by RR square plus X2 square. Again, we divide the numerator and denominator by X square. So the numerator becomes a 2 RR by X2 divided by RR by X2 whole square plus 1. This is nothing but a slip at a maximum torque. So 2 into slip at a maximum torque divided by slip at a maximum torque square plus 1. Thank you very much. If you have any doubt, you can ask me directly or you can ask me in the comment box of my YouTube channel, so that I am always welcome to answer all your